Ever wondered why understanding binary and permutation matrices is essential in mathematics, and how it can be applied in real life? Today, we're going to focus our attention on the intriguing world of binary and permutation matrices. These might sound like complex and abstract concepts, but they are, in fact, fundamental building blocks in the domain of mathematics. They are not just theoretical constructs, but have practical implications that permeate our everyday lives. Consider binary matrices. This mathematical tool is essentially a matrix with entries of only zeros and ones. Sounds simple, right? But here's the kicker. These humble binary matrices are one of the key foundations of computer science. Every time you type a letter on your keyboard or click your mouse, binary matrices are working behind the scenes, translating your actions into a language your computer understands. Now, let's move on to permutation matrices. These are square matrices that have exactly one entry of 1 in each row and each column, with all other entries being 0. They might seem a bit more complex than binary matrices, but their power and versatility are unparalleled. They play a crucial role in areas such as data analysis, where they are used to rearrange rows and columns of data for easier interpretation. Even more exciting is their role in cryptography, the science of coding and decoding information. Permutation matrices are used to scramble data, providing a key layer of security in our digital world. So, you see, binary and permutation matrices are not just theoretical concepts that live in dusty mathematics textbooks. They are dynamic and critical tools that drive our digital age, helping us to communicate, analyze data, and safeguard information. As we journey together through this topic, we'll explore these concepts in greater detail, providing examples and demonstrating how to perform calculations with these matrices. We'll also delve into their various applications, illustrating their relevance and importance in our world. So, buckle up as we dive into the fascinating world of binary and permutation matrices. First off, what is a binary matrix? It's not as complex as it sounds. In the realm of mathematics, a binary matrix is a square grid filled with zeros and ones. Imagine a chessboard where each square can be either black, represented by 1, or white, represented by 0. That's pretty much a basic binary matrix for you. The beauty of binary matrices lies in their simplicity and versatility. They can represent a wide range of information in a compact form. For instance, they can depict relationships between objects, track the presence or absence of features, or even map out intricate networks. Now, let's discuss some properties of binary matrices. They are defined by two key characteristics: rows and columns. The number of rows and columns determines the size of the matrix. For example, a binary matrix with 3 rows and 3 columns is referred to as a 3x3 matrix. One fascinating property of binary matrices is that you can perform basic operations on them, much like you would with numbers. You can add and subtract binary matrices of the same size, and even multiply them, though multiplication works a bit differently than what you're used to. Creating a binary matrix is as simple as deciding on its size, and then filling in the squares with zeros or ones. For instance, a 2x2 binary matrix could look like this. The first row is 1, 0, and the second row is 0, 1. Or it could be all zeros or all ones or any other combination of zeros and ones. But why are binary matrices useful? Well, they help us to translate complex data into a format that computers can understand and process efficiently. They are used in computer graphics, data compression, and even in the study of social networks. So, in a nutshell, a binary matrix is a simple, yet powerful tool in the world of mathematics and computer science. It's a grid of zeros and ones that can store, manipulate, and represent a wide range of data. Easy, isn't it? But hold on, there's more to come. Now, how about we do some calculations with binary matrices? Don't worry, you've got this. Let's first understand what a binary matrix is. A binary matrix is a matrix that consists of only zeros and ones. Simple, right? Now, when it comes to performing calculations with binary matrices, we primarily focus on three operations: addition, subtraction, and multiplication. Let's start with addition. Picture two binary matrices, both 2 by 2. We'll call them matrix A and matrix B. To add these together, all we do is add the corresponding elements in each matrix. The top left element of matrix A added to the top left element of matrix B gives us the top left element of our new matrix. We continue this for all pairs of corresponding elements. But remember, since we're dealing with binary matrices, any sum that results in a number greater than 1 needs to be converted back into binary form. Subtraction of binary matrices is also straightforward. We simply subtract corresponding elements in the same way we added them. However, in binary, there's no such thing as negative numbers. So if you end up with a negative result, you'll need to borrow from the next higher order, much like you would in decimal subtraction. Finally, let's move on to multiplication. Multiplying binary matrices is a bit more involved than addition or subtraction. It involves multiplying corresponding elements and then adding up those products. But don't forget, we're in binary world. So any product or sum greater than 1 needs to be converted back into binary. Let's take a moment to appreciate the beauty of this. Calculations with binary matrices may seem complex at first glance, but once you understand the underlying principles, it becomes a systematic process. And the best part? These operations are fundamental to many areas of computer science and data processing, making them incredibly useful to understand and apply. See? You're already getting the hang of it. Next up, permutation matrices. Sound complicated? Don't fret, it's simpler than you think. A permutation matrix is a special kind of square matrix that's made up of zeros and ones. But here's the catch. It has exactly one 1 in each row and each column, with the rest of the elements being zeros. So what makes these matrices interesting? Well, they have some unique properties. For instance, the product of two permutation matrices is also a permutation matrix. Additionally, the inverse of a permutation matrix is its transpose. That's right, just flip it over its diagonal, and you've got the inverse. Let's take a look at an example of a permutation matrix. Imagine a 3 by 3 matrix. The first row could be 0, 1, 0. The second row might be 1, 0, 0. And the third row could be 0, 0, 1. This is a permutation matrix because it has exactly one 1 in each row and each column. So, how do we create a permutation matrix? Well, start with an identity matrix. That's a matrix with 1s on the diagonal and zeros everywhere else. Then simply swap some rows or columns. And voila, you've got yourself a permutation matrix. But why are these matrices useful, you might wonder? Here's the thing. Permutation matrices are used in various fields, including computer science, engineering, and of course, mathematics. They're particularly helpful in rearranging the order of elements in a vector or the rows and columns of another matrix. This can be extremely useful in problem-solving scenarios where the order of elements matters. So, there you have it, permutation matrices. They're unique, they're useful, and they're not as complicated as they might seem. You've just taken a step further into the fascinating world of matrices. Still with me? Great, because there's just one more piece to the puzzle. Ready to tackle some calculations with permutation matrices? Let's do this. Permutation matrices are intriguing entities, especially when it comes to calculations. They might seem daunting at first, but with a little practice, they become as simple as pie. So, let's dive right in. First up, let's talk multiplication. When multiplying two permutation matrices, we follow the same rules as regular matrix multiplication. Remember, the product of two permutation matrices is also a permutation matrix. Think of a permutation matrix as a group of dancers, each in their own spot on the dance floor. When we multiply two permutation matrices, it's like telling our dancers to change their positions according to a choreographed routine. The result is a new permutation matrix, a new dance formation, if you will. Now let's take a look at the identity matrix, the wallflower of the matrix party. When a permutation matrix multiplies with the identity matrix, it remains the same. It's as if our dancers ignored the choreography and stayed in their spots. Finally, the inverse of a permutation matrix is its transpose. This is like watching the dance routine in reverse. The dancers go back to their original spots, and we're back to our starting permutation matrix. Keep practicing these calculations, and soon you'll be dancing your way through permutation matrices like a pro. And just like that, you've mastered permutation matrices too. Almost time to wrap up, but first, let's recap what we've learned. We've journeyed through the fascinating realm of binary and permutation matrices, understanding their definitions and exploring practical examples. We've uncovered